This is part two of my set of discussions on stability. I'll pick up exactly where I left off. I talked about the stability of under-damped second-order systems and covered the cases of stable, which is here, unstable, which is here, and then marginally stable systems, which is just the boundary case between stable and unstable systems. The next part of the discussion is about first-order systems, and they're simpler than second-order systems, obviously. There's a transfer function for a second-order system, a first-order system, sorry. And then the step response for the first-order system is given here as opposed to the one that we had above. And what you can notice about this already is that there's no sines and cosines in here, and you have to have complex poles to have oscillation. Complex poles come in pairs. So if you have a first-order system, you only have one pole, and therefore you can't have complex poles, and your system is non-oscillatory. Now, it can be stable or unstable, and if we look at our system here, we have a enduring part, which is our steady state. This is our response. We have an enduring part, which is the 1 here, and then if we have a positive time constant, and which is normal, and then time runs forward, then this exponent of e will be negative because the big T and the little t are positive, and therefore it'll die off. Okay, but as t goes to infinity, then this part gets to be, this part dies off, and we're left with simply YSS, or y at infinity is equal to KSS. But it could happen, actually, that t turns out to be negative. Now, that seems odd because the time constant is the time that it takes a system to respond. But various things can happen that basically produce, if we look at our transfer function, produce a negative number right here as a coefficient of s. We can look at the two possibilities of a stable system and an unstable system, first order. The graph on the left should actually look fairly common or usual. This is a normal first order. You put in a step function and the system jumps up, although not immediately. It takes some time to respond. And if we put in a unit step and it jumped up to 5, that would mean that it had a gain of 5. But the other case is where it blows up. And so if t happens to be negative for one reason or another, you put in a step function and the system just goes haywire, and over time it will go to infinity. Okay, now, to evaluate stability, you can look at the transfer function of the system. And there's a whole science about this that I'm not going to go into great detail about. There's what's called the Routh-Hurwitz stability criteria, and you develop this thing called a Routh array, and you analyze it to look and see whether your system is stable or not. Remember, what we're looking for is we're looking for the existence of any pole in the right half plane. It only takes one to make your system blow up, and up above, as you can read, you'll see that you could have a thousandth order system. So the system has 1,000 poles, and 999 of them could be in the left half plane and therefore stable. But if one is in the right half plane, then the system is unstable. So all of the poles have to be in the left half plane. Now, I talk about the fact that one of the necessary conditions for stability is that you can't have any sign changes in the denominator of your transfer function. So we can look at all of these systems and gauge their stability. These are different systems here. And actually it says all of these systems are stable. So what we're looking at, we don't care about the numerator at all. Whether it's positive or negative doesn't enter the picture, or doesn't play a role as far as the stability goes. It'll determine whether the system goes up or down, but it won't determine whether the system blows up or not. And what we're looking for is we're looking for sign changes, not negative signs, but sign changes. So all of the coefficients in the first transfer function are positive. There's a positive 1 here, which we don't write, then plus 18, plus 52. Here we have the same thing, although we have a negative on top. But as I said, that does not determine whether the system is stable or not. It just determines which way it's going to go when you put a positive step in. Here, it looks like, oh, this may be an unstable system because I have negative signs here. But actually, this system here is exactly the same as the system here. If I multiplied this by negative 1 over negative 1, I would wind up with the system before, the second one. Here is a first order system, both the time constant, well, this is not the time constant because you need to have a 1 here for this to be the time constant, but the coefficient of S is positive, positive 18, and the coefficient of S0 is what it is, but the constant term here is plus 2, so since you have two pluses, you have no sign change. Here we have no sign change also because both of them are negative. Okay, so all of these systems are stable. And you get into, when you're gauging stability, what are called necessary conditions and sufficient conditions. So you may want to go read up on those. You can Google those if you want to. But a necessary condition for stability, so this has to be true if you're going to have a stable system. No sign changes in the denominator of the transfer function. That is a necessary condition. So if you see sign changes in the denominator of the transfer function, you can say automatically this system is unstable. Stop. No more analysis needed. Okay? Now, but that is not a sufficient condition. So what that means is that if it occurs, if you have sign changes, then the system is unstable. If you don't have sign changes, that doesn't mean that the system is stable. It means that it can be stable, but then there are other conditions that you need to meet, or that the system needs to meet, before you can conclude that the system is stable. So no sign changes is a necessary condition for stability, but it is not a sufficient condition for stability. So let's look at what we have for sufficient conditions. And actually it's easy if you have a first and a second order system. There are no additional conditions necessary, and so for a first and a second order system, if there are no sign changes, the system is stable. So the no sign change condition is both necessary and sufficient for systems that are less than or equal to order 2. Now all of this, like I said, there's a science behind all this. I'm just giving you the rules because the science is a little bit arcane, and you could learn it if you want to, but if you just follow these rules, then that's all you need to determine whether a system is stable or not. Once you get up into order 3 and more, then things get to be a little bit more complicated. And what I've done is given the conditions for stability for systems of order 5 and less. You hardly ever run into a system that's greater than that. What happens is, if you have a system that has a high order, often what you do is you can ignore parts of it, the really fast poles, as we say. They're the ones that decay very quickly. And so you focus on actually the first 1, 2, 3, or in this case 5 poles. If you need to go higher than that, then you'll have to go back and look at the whole discussion on Routh Hurwitz stability criteria. But what I do is I give it for orders of 5 and down, and that should suffice for most of the work that you do. So if you have a third order, so what we're using is we're using this polynomial here as a pattern. If you have a system of 3, n equals 3, so these terms would be gone. A4 and A5 are 0. And you have a third order polynomial, then you have to meet this criterion here. Okay? A0 times A3 minus A1 times A2 It's got to be less than 0. So if you have no sign changes and you don't meet this sufficient condition, then your system is unstable. If you don't have sign changes, they get you in the ballpark, and you do meet this criterion, then you have one of those systems with no sign changes, but it meets the sufficient condition, so it is stable. Now, things get more complicated as you go higher. You have, for n equals 4, you have higher or more complicated criterion here for your sufficiency. When you go to 5, you actually have 2 conditions that you have to meet. So as you can see, if you went to 6, 7, and 8 and you develop the criteria for them, they're going to be even more complicated than this. So I'm going to stop here because we're over 10 minutes. But like I said, what's important here is you have a necessary condition, no sign changes in the denominator of the transfer function. If the order is 3 or greater, then you have other conditions which give you the sufficient conditions that will tell you whether your system is stable or not. Okay, I'll stop here and start up at this point also.